Greetings and welcome, friends. Hopefully the audio is a little bit better for you today. Changed some of my levels. Here we go. We're talking about section 1.2 in our geometry book. Measuring stuff is what it's called, I think. And here we go. We're going to jump right in. This is from Big Ideas, the Common Core book. And here it says, in geometry, a rule that is accepted without proof is called a postulate or axiom. A rule that can be proved is called a theorem, as you will see later. There you go. Not right now, but later. So postulates are supposed to be so apparently obvious that we just accept them as true. Okay? So in geometry, the way we've got this, we've got a handful of kind of definitions and postulates. And really most of mathematics works this way, where then we combine those, we synthesize those ideas, and then prove theorems. And we build in our understanding by combining previously known knowledge. And so that's how math is discovered. It's somewhat innate within our universe. So we just kind of keep discovering new things. That's how math can be independently discovered by different cultures over different time periods. That's one of the reasons why calculus was near simultaneously discovered in two different countries by two different people that were alive at the same time. And there was a question whether one stole the other's work, but neither did. They both independently discovered calculus, and they actually approached it from different results. Somewhat interesting. So math is a universal language as a result. It's something that I know I have a math professor that argued regarding our, SETI, the Search for Extraterrestrial Life, or any of the, programs where we send like a probe way out into space. Like as far as if we wanted to identify ourselves as being an intelligent species, that we would communicate with the universal language of mathematics. And in fact, some of those things have been done. Not that we've discovered aliens, but that we've sent out signals. Okay, so here we go. So here's a postulate. Your book is referring to this as postulate 1.1, called the ruler postulate. The points in a line can be matched 1-to-1 with real numbers. Real numbers. How many are there for the real numbers? Well, there are infinitely many real numbers. So we're not talking about just like numbers like the integers or whole numbers or the natural numbers. Or irrational numbers. We're talking about all of them. All the ones except the non-real numbers, the imaginary ones, which maybe you didn't realize there were imaginary numbers. I'll save that for Algebra 2, when you'll discover about non-real numbers. So right now for you, real numbers are all the numbers you can ever think of. The real number that corresponds to a point is the coordinate of the point. I find that interesting, actually. Well, no, I guess these are two-dimensional sketches. But if I'm referring to a number line, is coordinate appropriate? Shouldn't it just be the ordinate? Because there would only be one value, one numerical value for it. But I don't know. That's fine. The distance between points A and B, written as AB, okay? So distance, this is now a number. All right, it's not the sketch, it's a number, is written as AB. And it is the absolute value of the difference of the coordinates of A and B. All right, so here's the names of our points. Here's our sketch. The coordinates of the points might be some numerical value if we're thinking about a number line. So this might be at like 7. This might be at, 20. And what this is saying is that the distance between these 2 points can be calculated by taking the absolute value of their difference. So 20 minus 7, absval, so that's absval of 13, which is 13 in this case. Right, 13 is the absolute value of 13 because, does anyone know the definition of absolute value? I mean, even in layman's terms, like what does an absolute value do? Yeah. The distance a number is away from 0, as we talked about earlier, pre-video for my VIP mathematicians, distance is always positive. So absolute value of a positive number will continue to be positive, and absolute value of a negative number will make it positive. So we would refer to this distance as then 13 units apart. Okay, so this is called the ruler postulate. Hopefully you believe that's true. I don't know what to tell you, right? It's just supposed to be assumed to be true. So let's do an example of this. This is a little bit further down there. So here, you guys might just need to follow along a tad here, because you might not have said rulers or whatnot. But that's okay. You could draw a line and you might have a ruler on hand, and you could try doing a similar thing. So let's say that I have a ruler. Now, if I wanted to measure the length of ST, we would probably do this, right? Where I'd try my best to line up one of the points being at 0, and then I would measure it to, you know, whatever point T happens to land at. Which that does work according to the ruler postulate. I would do, the coordinate of T would be, I don't know, 3 7/8. The coordinate of S would be 0, and 3 7/8 minus 0 is 3 7/8, and the length is 3 7/8. However, what's interesting about this postulate is it does not assume that you start with 0 at one end. Let's do, I don't know, like this. Okay? So if I line this up here, S appears to now be at 1.5, and T appears to be at, let's see, I'm just going to give this a decimal value. Let's call it like 5.4, even though I know that's not how it works. And so the distance, ST, the length of ST, is going to equal the absolute value of 5.4 minus 1.5. Okay, so this works even if I don't have it starting at 0. All right, I don't think that necessarily would have been like, oh, like, you know, that's interesting, because I don't think that's how we ever would have measured it ourselves, but it does work this way as well. Let's see, so 5.4 minus 1 would have been 4.4 minus 0.5 would have been, what, 3.9, and absolute value of 3.9 is 3.9. In this case, these say centimeters. Oh, wait a minute. Yeah, so these aren't sixteenths. I said sixteenths earlier. I assumed these were inches. I should have counted. But yeah, so this would be 3.9 centimeters. Centimeters, yes. So yeah, so the ruler postulate, that's how you could use it. I'm not going to have us do any more of that right now. But let's talk about construction. Not in terms of building buildings, although geometry is often used in the world of construction. There's also some cool shorthand tricks that you can learn doing construction that applies geometric principles in a nice kind of on-the-job way. Actually, you probably could learn some of those skill sets at the Career Center located in Brattleboro, Vermont, right? Career Center of, what, Windham County or something? I don't know. It's okay. People know I'm on the internet. I'm the only Brian Waddy on the planet. So if you search Brian Waddy, I'm it. Like, they'll know, they know where I live. It's okay. Actually, also, yeah, don't tell people where I live. My life has been threatened once. Interesting. Never mind. Nah. So, construction is a geometric drawing that uses a limited set of tools, usually a compass and a straight edge. Okay, interesting stuff. Interesting stuff. So we're actually going to do some work with this a little bit today. So a straight edge, usually you would just use something like a ruler. However, you also have, you could just use something that literally is straight, because we're not measuring it in some of these cases for construction. So let's try this construction setup right here. I'm trying to think of a way I can simulate this. What I might have to do is just draw it old school here. Here we go. Here we go. I'm going to document camera this. You guys ready for this? All right, get ready to see some excellent internet hand modeling. Ooh, that's right. I am married. So, yeah. there is a Mrs. Waddy, although she does not have a YouTube channel. So here we go. Let's say I've got, here's my little segment that I want to construct. One of the ways I could do this, yeah, you could probably say, well, can't I just measure it and then, you know, take that measurement and then redraw another segment of that length? And yeah, that could work, but we're talking about using tools, straight edge and a compass. This is actually an interesting little compass guy. This is like, it's got a ruler, so it's got a straight edge. It has a compass component where I'm able to, oh, this marker won't work. No, I'll have to use a pen, but that's okay. So it has a compass functionality. A compass is just got a fixed point, and then it kind of moves along the length of an arc, where you guys might not know this, but the definition of a circle is the set of all points such that they are equidistant from the center, and that distance is the radius. So if I want to construct a line segment of same length, what I could do is line up my compass here, and this is, I know, like a funky compass right here, and I'll pick a point for one of my starting points. I'll line that up right here. Wow, this one even has like this cool little like scoping it in right thing here. I'm not going to no scope this. And then I draw the arc like so. And so now if I draw using the straight edge from that endpoint to anywhere on that arc, I have now constructed a segment of identical length that looks like 1 1/4 and, oh sorry, 2 1/4 and 2 1/4. There we go, 2 1/4. So that's one of the ways you can construct using tools. More typically, you would have, right, just like a ruler like such, and a tool like this. These things are dangerous, though. We don't trust you with sharp things. Where you can kind of set the width, you tighten it to fix it, and then you draw along an arc like so. Something to that effect. So that's how you can do constructions. We're going to do a variety of them later today. And yeah, so that's construction, because geometry is a language of both you know, symbols as well as diagrams, and so we're going to want to be able to do that at different points. So let's see, let me skip back to this. So that was just a basic construction. You guys will have a chance a little bit later in class today to do some more. And here's an interesting thought. We're calling these congruent segments. So congruent segment. So there's going to be ways that we denote this using symbols. We're going to recognize this using diagrams. We're also going to recognize kind of talking about the numerical quantity that represents their length or distance. All right, so this notation is going to be important. So check this out. Line segments that have the same length are called congruent. Notice congruent is not the same as equal. All right, not the same. It's not equal to equal, is what I just wrote, oddly enough. Congruent is referring to kind of the same size and shape, is kind of my general definition for this word congruent, okay? You can say that the length of AB is equal, and I want to point out that does not mean congruent to the length of CD. All right, so if I'm referring to lengths that are equal, this is a number that is equal to a number. Numbers can be equal, but our diagrams are congruent. Shapes can be congruent. Angles can be congruent. Segments, in this case, can be congruent. Equality is used to relate numbers that are the same. Congruence is used to relate diagrams or images or, right, shapes, polygons that are the same, okay? Or you can say that AB, the segment AB, is congruent to segment CD. The symbol, it's an equal sign with like a little toupee on it right there. Like, so, oh wow, it's like, wow, equal sign, you're looking really great. Are you back on the dating market? There's something different about you. I can't tell. Wow, you're really putting yourself out there. That's great. And so that is the symbol congruent, which is not equality, but notice it does, there's some similarities to equality. Actually, math joke, here's the symbol for similarity, and I just said similarity to equality, and that's like kind of like if similar symbol was the mom and equal sign was the dad, like congruence, bam, right there. It makes sense. These mathematicians are great. So here's how you could refer to their measures being equal. Here's how you can refer to the segments being congruent. And graphically, the way we denote congruence is with these little tick marks. So if I have two segments that are congruent there, I would say AB is congruent to CD. That's a graphical representation. If I have more than two things that are congruent, but that are not congruent all to each other, you can then do kind of double tick marks. So for instance, AC is congruent to BD. All right, so this is going to be a big deal. I know it seems like, well, what's the big deal? Why can't I just say equals all the time? But mathematically, it's going to be significant that we use the right terminology at different points, because we're going to be kind of swapping back and forth at different times. Let's see, here we go. Let's do an example. So let's see, comparing segments for congruence. Let's see, plot these points, looks like JKLM, in a coordinate plane, then determine whether JK and LM are congruent. Okay, so for plotting points, you guys might remember coordinate plane stuff. You have an x-axis and a y-axis, and then you do equally spaced tick marks. Positive x's over here, negative x's over there. Question, comment? Nah, you'll be fine without it. Just follow along for this moment, because watch this. I'm going to fast forward. Like, first I draw this realistic head, and then I erase some of its more detailed features, and then check out what happens here. Oh wow, look at that! Look at that amazing sketch I just did. Wow, guys, did you see that? I'm just super impressed with my drawing abilities. So when I plot points, just to review that concept, because that'll be helpful. The first number is the x-coordinate, the second number is the y-coordinate. By the way, ordered pairs or ordered triples are always given in alphabetic order by variable name, unless those variables represent like a specific unit. Oftentimes, you could have, for instance, like time, and now I can't think of a letter after T that would represent a variable of a real-world problem. But time is often always going to be your x-axis, even if it's non-alphabetic. So letters after T could happen like that. But here we go. So to plot a point, -3, 4, I start at, you guys remember what this intersection of two lines is called? The origin. Wow, that's right. So I would move left 3, a 1, a 2, a 3, crunch, and 1, 2, 3, 4 up, and there is that point right there. And then 2, 4, I'd go over 1, 2, up 4. 1, 3 is over 1, up 3. And 1, -2 would be over 1, down 2. So the question is, are these segments congruent? So in order to do that, I'm going to use, later on we'll have a different formula for two-dimensional measurements, but notice these are conveniently battleship-oriented, either horizontally or vertically according to this coordinate plane. And so I can actually use the ruler postulate from earlier. So which coordinate is the horizontal coordinate for these 2 points? Which is the horizontal coordinate for this point? The -3 or the +4? Let's see. The -3 and the 2 is the horizontal component. So if I want to measure this distance, all right, I'm going to be subtracting those 2 things. So let's see. So JK, without the line on top, is referring to its distance or length, is going to equal to the absolute value of 2. I could either do 2 minus -3 or -3 minus 2. It won't matter. The absolute value will take care of it. By the way, absolute value is distributive. You have to do the inside before you do the rest. Unless, never mind, I'm not even going to give you any exceptions. I think I could argue like multiplication in some instances, but not for subtraction. So 2 minus a negative 3 is 2 plus 3. And 2 plus 3 is 5. Abs 5 is equal to 5. Let's do the same thing for L and M. Now this one's vertically oriented, so their vertical coordinates would be the 3 and the negative 2. So LM is going to equal the abs val of 3 minus negative 2. Oh, guys, I've got a good feeling about this. 3 plus 2, double negative, right? Subtracting a negative is the same as adding a positive, my friends. And 3 plus 2 is 5. Abs val is equal to 5. If their measures are equal, what do you think we can conclude? The segments are congruent. All right, so segment JK is therefore congruent to segment LM. All right, because they have the same length. Their measures were equal, therefore the segments are congruent. All right, let's see. Let's get one more big idea in here. Aha. Postulate 1.2. That means you need to believe this is true because I'm a cult leader and you need to trust me. But also it should be somewhat obviously true, I hope. That's what postulates are, okay? So we're not going to prove postulates. It's just like, yeah, that makes sense. I don't think we can really, like, I can't reduce this to simpler things to have it not be a postulate. Let's see, so it says this. If B is between A and C, then AB, so that's referring to the numerical number, plus BC, this length as a number, right, equals the right symbol? Should they have used congruence? Equal is the right symbol because we're talking about numbers here. This is a number, this is a number. Equals AC, the length of the whole thing. So the big part is equal to the sum of all the little non-overlapping parts. Okay? And then let's see, it says if AB plus BC is equal to AC, wow, this is like kind of said in the opposite way. It says then B is between A and C. That second part, wow, do I like that. It's delicious. Wow. I just want to let my brain chew on that for a minute. Wow. Huh. So check this out. Let me consider this second part first. So if I have A, B, and C, let's assume this. And what if I said this was 3, and this was 4, and this was 7? And I'd shown that 3 plus 4 equals 7, right? And now they're saying, therefore, B is between A and C. Why do you think that's true? Does my sketch make sense anymore? Is my sketch to scale? I mean, it wasn't really to scale to begin with. That 3 and 4 looked near isosceles when I made this triangle, but why could B not be off of the line segment AC? Well, think about this. 3, if 3 units away was here, and I drew like my arc, and 4, if I drew like my arc, here's all points that are 4 units away, and if these were all units that are 3 units away, there's only one spot where 3 and 4 would cross each other from those two endpoints. If I drew this with my compass, it has to be there, because once I go off the line, this has to be longer than 3. This would have to be longer than 4, right? That's the only way it's possible to arrange it. Yeah, it can't happen, right? The shortest distance between 2 points is a straight line, and if 3 plus 4 is exactly that distance, then they are in a straight line. So I like that. I like that. I'm giving this a like. I was going to try to draw a thumbs up, but then I was like, no, I'm not going to do that. I don't know how. I'm not an artist. But more significantly, the one that we will use more often is we'll have a sketch where we know that B is already on that segment, and then we will conclude this to be true. And now we can use this in a variety of different ways, like so. All right, internet friends, hang in there. Here we go. All right, here's 2 examples. So it says find DF. So DE is 23, EF is 35. Therefore, according to the segment addition postulate, I would assume that DF, its length, not the image, is equal to, so I'm not using congruent here, 23 plus 35. Right, so that's what, 55? No, 58. Yeah, thank you. Whew. Good save, good save. All right, ooh, this one's interesting. Let's describe this length, GH. Let's give it a numerical value of x. So according to the segment addition postulate, I would have had said FH is equal to FG plus GH, right? And now if I substitute, I know FH this time, 36. I know FG, 21, but I don't know GH. I could have left that in terms of GH, but we'll just call it X in this case. How can I find the value of GH? What can I do to figure out X? Subtract 21 from both sides. That's right. Subtraction property of equality, friends. So I'm also going to reflexive property this. So it looks like 15. So let's see, x equals 15, which I guess isn't my final answer because I'd have to convert that back to GH speak. GH is equal to 15. So sometimes you can even use this property in somewhat reverse, and you just combine it with some of your old school algebra skills, and you're good. You're golden, friends. All right. Well, I think that's all we can fit for today. So thanks for watching, internet friends. Always a pleasure. Bye-bye.